Okay, so in this video, we will start a review of basic probability. Starting with the definition of probability, which is that the probability of event A happening is equal to the number of elements in set A divided by the number of elements in the entire sample space. We set it up as a fraction, and we can leave it expressed as a fraction or convert it to a decimal or percent. For example, if it's 9 out of 15, you could reduce that to 3 out of 5. You could express that as the decimal 0.6 or as the percent 60. Any one of those would be acceptable. Most often you're going to see a reduced fraction for final answers for probability. Here's an example of calculating simple probability. So if the experiment is rolling a fair dice, then our sample space is going to be the numbers 1 through 6. Those are the options when rolling the dice. And so then we're looking for the probability of each of these events. So I will scroll through our answers here. The probability of rolling an odd number, so if the event rolling an odd number includes 1, 3, and 5, then there are 3 possibilities there out of 6 total. And so the probability of rolling an odd number is 1/2. Probability of rolling an even prime number, there's only one of those. The number 2 is an even prime number. And so the probability is 1 out of 6 because there's only one way to do that and there are 6 options altogether. Probability of rolling an odd prime number. So the odd prime numbers in 1 through 6 include just 3 and 5. 1 is not considered a prime number. And so there are 2 possibilities out of 6 for a probability of 1/3. And then the probability of rolling a number that is either prime or even. So this is a sort of a joint list of the primes and the evens that are in this set, because you're looking for the probability that the number you're looking at on the dice is either a prime number or an even number. So that could be a 2, 3, 4, 5, or 6. So a final probability of 5/6. Some facts about probability. The probability of any event is going to take a value from 0 to 1. 0 means certain to not occur, and 1 means that it is certain to occur, and then every value in between for probability. So we tend to leave them as fractions like 3/5. You should never get a fraction with a value greater than 1, like 5/3. That would not be a reasonable probability. All possible outcomes together have a probability of 1, or you could think about this otherwise expressed as the probability of getting something in the sample space. If you reach into the sample space and pull something out randomly, you're certainly going to get something in the sample space. So the probability of getting something in S is 1. For disjoint or mutually exclusive events, these are 2 events that don't overlap at all. So like A could happen or B could happen, but there's no way that they could happen at the same time. The probability of either one or the other happening is just going to be the sum of their separate probabilities. So there it is expressed as a formula. And there's a visual to help you understand it, that if A and B are separate circles in a Venn diagram, they do not overlap at all. If the probability of A happening is 0.2 and the probability of B happening is 0.7, then the probability of A or B happening overall is 0.9, because there's only a 0.1 chance that neither will happen. So there's a 0.9 chance that either A or B will happen. Here we have an experiment in which a coin is tossed and a dice is rolled. Pull up this screen shade. It's asking us to draw a sample space diagram and then find the probability that in a single experiment you obtain a head and a number less than 3. This is the word and, not or, so that's going to change the way we think about our final answer. First, we want to draw the sample space diagram. So this just means that sometimes it's easier to sketch a figure of the sample space rather than make a long list. So here, if you're doing a coin toss and a dice roll at the same time, you could think about this sort of grid of heads, tails as your 2 options for the coin toss. 1 through 6 is your options for the dice roll. And then the purple would be our sample space. So H with a 1, H with a 2, H with a 3, and so on for all the heads. Tails with 1, tails with 2, tails with 3, and so on for all the tails. So there end up being 12 things in the sample space. You can come up with any diagram that will represent the sample space. So a sample space diagram doesn't always look one sort of way. It just means a diagram rather than a long list, because it's a little bit easier with some situations. So the ones circled in red are the ones that meet the condition of a head and a number less than 3. So that means at the same time, right? If you do both of these things in the same experiment, you're looking for a head and a number less than 3 on the dice. So that would be the H1 and the H2. and none of the other options in our sample space fit those conditions. So the probability of getting ahead and a number less than 3 is 2 out of 12. It did not say the probability of getting a head or a number less than 3, because then we would have had to include all of the heads and all of the dice rolls that were less than 3. It specifically said and, so that means we're looking for these situations where both are happening at the same time. Another note about probability, the probability of an event not happening is equal to 1 minus the probability of the event happening, and vice versa. So these would be called complementary events, and in the picture I show, there's only one circle inside this Venn diagram, and I'm labeling it A. So that means everything outside of A we would call the complement to A, or A prime. And of course, the probability of everything that's not in A has to be 1 minus 0.3 in this case, or 1 minus the probability of A, because the remaining piece has to be outside of A. So that should make sort of inherent sense. A simple example of a probability table, in case you're quizzed on one of these. We have a password generator choosing the first digits of its passwords with the following probabilities. It is worth calculating in a table like this the sum of all the given probabilities, because if it doesn't add up to 1, that means there's some missing data from this table, which could come into play in the questions that are being asked. But indeed, if you add up all these decimals, the total probability is 1. So that means all of the options we're choosing from are 2, 5, 6, 7, and 9. There are no other choices that are not shown. So to find the probability that the first digit chosen is even, I just need to pull out the even probabilities. So 0.16, because that's the probability of the first digit being 2, which is an even number, and 0.37. And because these are disjoint events, there's no way the first digit could be a 2 and a 6 at the same time, right? These would be 2 separate circles on a Venn diagram. Then I can just add those 2 probabilities together. The first digit is even, will be 0.53. Next question. First digit chosen is not smaller than 6, so that would mean 6, 7, or 9. Add those probabilities together, 0.73. And probability that the first digit is 5 or 7, add together the probability of 5, probability of the 7, and it's 0.32. And the last thing in this review, or this section of the review, is tree diagrams, and we'll do more of these throughout, but this is our first taste of them. So a tree diagram is a visual way to represent simple events, particularly helpful if you're doing one event followed by another event, like rolling a dice twice in a row, or pulling a sock out of a drawer and then pulling another sock out of a drawer. So you're doing an experiment and then doing another experiment right after, or maybe 3 experiments in a row. Tree diagrams are very helpful for that. But you only want to use a tree diagram if there aren't many outcomes. So like, if I was rolling a dice and I'm wondering whether I'm going to get a 6 or not a 6, I could use a tree diagram to show those 2 possibilities, right? Getting a 6, probability is 1 out of 6, or getting not a 6, that would be 5 out of 6. Or in those classic scenarios of pulling a marble out of a bag or socks out of a drawer, it may have 3 different colors given. And so I want to know, if there's 10 marbles in the bag and 2 of them are blue and 1 of them is red and 7 are yellow. So there's not that many outcomes that could happen. It's either blue, red, or yellow, and you can list the probabilities along the branches. What you don't want to do is something that has, 6 possible outcomes. Like I roll a dice and I want to know the probability of getting a 2. Well, a tree diagram for that would have to have 6 branches, right? It would have to have the probabilities of 1, a 1, a 2, a 3, a 4, a 5, a 6. And so it's not going to be that helpful to have a tree diagram when there are that many possible outcomes. So you just have to think carefully about whether a tree diagram is really the most helpful way to represent the scenario that's happening in the question. So for example, here 2 fair dice are being rolled, one after another, 1 red and then 1 blue. And so this is that sort of 2 experiments are happening. I'm rolling a red dice and I'm rolling a blue dice, so it seems to lend itself to a tree diagram. But dice you should be a little bit scared of because there's so many possible outcomes, right? But if you look at all the questions in A, B, C, and D, they're all talking about either rolling a 6 or not rolling a 6. And so when I set up this tree diagram, it's going to look like this. The red branches show the roll of the red dice, and the 2 possible outcomes for that are going to be a 6 or not a 6. And then let's say I've rolled a 6. Well, then after that, when I roll the blue dice, there's 2 possibilities for the blue dice, and that would be a 6 or not a 6. And then for the other branch, right, let's say I didn't roll a 6 on the first go on the red dice, then I can roll the blue and still have the options of either a 6 or not a 6. So this diagram represents all the possible paths, right, of rolling a red, then rolling the blue. And so I can answer the following probability questions. What's the probability that a double 6 is rolled? So a double 6 means that I've traveled down the path of rolling a 6 for the red dice, followed by the path of rolling a 6 for the blue dice. And in the end, the probability of that branch happening will be to multiply the probabilities along the way. So I've illustrated that here with this green line. That I'm going to multiply the 1/6 from the red branch times the 1/6 from the blue and get 1 out of 36. This means there are 36 possibilities overall, and so only one of them is a 6 followed by another 6. So the probability of rolling a double 6 is 1 over 36. Probability of getting no 6s, right? So this is going to involve the branches that have not a 6, followed by not a 6. And this is the only pathway that will get me no 6s, right, on either the red or the blue dice. And that's a 25 out of 36 chance of happening because there's so many options for not 6, right? Could be a 2, 3, a 1, 5, 4. So 25 out of 36. Probability of getting exactly 1/6. This one's a little interesting. So exactly 1 means that I either rolled a 6 on the red and then not on the blue, or not a 6 on the red, but then I did roll a 6 on the blue. And so I've calculated these two branches. Each one of them is 5 out of 36. And so then I can add those two together, 5 over 36 plus 5 over 36, to get a 10 out of 36 chance that either one of these pathways is going to happen. So on tree diagrams, we multiply to get to the end of the branch, but then we add different branches together if more than one branch is going to satisfy the conditions of the event. And then probability of getting at least 1/6 involves a whole bunch of branches, right? The 6 followed by a 6, 6 followed by not a 6, or the not a 6 followed by a 6. So I can add those 3 branches together. Or you can think about the probability of getting at least 1/6 is going to be everything other than the not 6 pathway. So you can think about the alternative approach to this. The probability of getting at least one of something is going to equal 1 minus the probability of getting none of that thing. That's sort of the notion of the complement. And so you can get to the same result by doing 1 minus the 25 over 36 that we had from question B up above. And for now, that is all.